In this video, we will take a look at the hypothesis test for two independent population means. I'm going to go through some of the general ideas and overviews for the hypothesis test, and we'll take a look at an example where I explain a little bit more in detail the process for hypothesis testing and also give you some ideas on how we look at a scenario and perform the hypothesis test. So first off, just to recall, the reason for doing a hypothesis test is we want to evaluate a claim about a population parameter. It just happens to be in this context, we're looking at the difference between two means. So we're going to focus on what's called the independent samples T test, and we'll focus even more specifically on the unpooled version of that T test. So there's a couple things that we have to know first, and these are the conditions or the assumptions that pertain to this particular hypothesis test. So when we're dealing with independent samples, the first assumption is that we have a quantitative variable from two independent groups. Or two independent population means, mu1 and mu2, and we have to be able to define those in context. The second assumption or condition is that randomization is used to gather the data. Remember, we do this to help eliminate or reduce sampling bias, and also to ensure that the sample that we select resembles the population. And then the third assumption is the sample size is at least 30 for both groups. So in other words, N1 and N2 both have to be at least 30. If we don't satisfy that part of the condition, there's another part of it that says, or the population distribution is approximately normal for both groups. Okay, so if we don't meet the sample size requirement, we would check the population distribution. And generally, we don't have the population distribution. So what we do is we take a look at the sample and see if that appears to be approximately normal. So when we talk about the test, there's three types of tests that we typically look at. We have the left tail test, the two tail test, and the right tail test. Now this is a little bit different because we're comparing two means in this case, or two independent groups. Now I typically like to write my hypothesis statements like you see here in the black, where I'm comparing the two by using an inequality in between those. And the blue is an alternate way that those can be written depending on the text or the professor that you have. So again, I will always focus on the complement rule in my class, but there's also situations where you want to use the hypothesis statements that you see below right here where my cursor is, okay? So with a left tail test, what defines the left tail test is that our alternative hypothesis says the population mean for group 1 is less than the population mean for group 2, and that less than sign tells me I'm doing a left tail test. So that's going to be the area of my rejection region and the area where my value of alpha goes. And then if you think about that, think along that same logic, right tail test is going to have an alternative hypothesis that says the population mean of group 1 is greater than the population mean of group 2. The arrow in H sub A is pointing to the right, so therefore we have a right tail test. That's going to be our rejection region and our alpha value. And just like before when we talked about this, when we have the not equal to sign in H sub A, remember not equal to remembers our population mean of group 1 could be less than the population mean of group 2, or the population mean of group 1 could be greater than the population mean of group 2. So it just means it's different than, mu1 is different than mu2. And in this case, we have a two-tail test. So now when we calculate the test statistic, there's actually three different options that you'll see depending on your professor and your textbook. So there's actually a fourth condition that we would look at, and that is, do we know what sigma 1 and sigma 2 are, or don't we know what they are? Okay, and there's another part of the condition we'll talk about as well. But if we knew sigma 1 and sigma 2, we would use the z-test statistic in order to complete our hypothesis test. We're not going to focus on that in this class or this lesson at all. If sigma 1 and sigma 2 are unknown, but sigma 1 is equal to sigma 2, we would use what's called the pooled T test. Now, in order to perform the pooled T test, we actually would have to do another hypothesis test called the F test to compare the two variances and determine whether they are equal or they are different, okay? So we're not going to do that one. We're going to focus on this last one right here where we make the assumption that sigma 1 and sigma 2 squared, the population variances are unknown, and sigma 1 squared is not equal to sigma 2 squared. That's called the unpooled T test. So that's what we'll focus on with this one. And the test statistic is as follows that you can see right here. Now, the degrees of freedom, this is the approximation for the degrees of freedom. It's essentially a weighted degrees of freedom based on the variability. And it seems very difficult to calculate. It's really not that bad. It just takes a little bit of work, and then also a lot of accounting on our values to make sure that we're not plugging in the wrong values in the wrong spot. Another way that's a little bit more conservative for estimating the degrees of freedom is taking the minimum of the 2 degrees of freedom from the 2 independent groups, whatever the minimum value is. So whenever we do a hypothesis test by hand, we will always use this. But be aware, if you do a hypothesis test on your calculator or you use statistical software, it is going to give you this degrees of freedom right here, this big messy calculation that you see right there for the unpooled degrees of freedom, okay? So the reason I highlighted this is because we're going to focus on the unpooled T test. So we'll be using this test statistic and then this degrees of freedom down here specifically in the example. So now that we have a little bit of information about kind of some of the general ideas or general components of the hypothesis test, let's take a look at an example and go through step by step what we're doing, okay? So in example 1, it says we're studying STEM test scores in education, and we'd like to know if males perform better than females on average. All right, so maybe we think there's some sort of gender effect going, and we want to see whether or not there's something to do with gender in the performance on these tests. So we took a stratified random sample by gender, and the data that I used has 0s and 1s. This is pretty common if you have to type in gender. We might use a numeric value to represent one gender and another numeric value to represent the other gender, and we're going to use 0 and 1 to represent females and males respectively. And those are the scores from the STEM test score, all right? So this is the data right here. So all these 1s represent the male's test scores, and all these 0s next to the test scores represent the female test scores. So this is typically the way that we might see the data structured if we were bringing it into SPSS or any other statistical package. And we're going to use an alpha equal 0.05 level of significance to evaluate this. So over here on the right, I have the group statistics already summarized. So I have the females, there was a sample size of 7, a mean of 78.71, a standard deviation of 5.187. And then for the males, we have a sample size of 9, we have a mean of 81.11, and a standard deviation of 13.308. And we're going to ignore the standard error on the mean right now. We're not going to use that for anything with what we're doing in the next few steps, okay? So we have our summary statistics. We have our raw data right here. Now we have to go through and look at this step by step. If you recall, step 1, when we deal with the assumptions are a series of questions essentially that we have to go through and be able to answer in order to use a specific hypothesis test. And these assumptions are specific to the independent samples T test or the unpooled T test, which we're going to be looking at. So the first thing that we have to satisfy is we have to have a quantitative variable for 2 independent groups. So in this case, the quantitative variable is the test score of each of the individuals that took this STEM test. The independent grouping variable is the gender, which would be male or female in this case. That's how we're grouping them, and males are independent of females. Mu1 is going to represent the average test score for all females, and Mu2 is going to represent the average test score for all males. The second condition that we have is that randomization has to be used to gather the data from both groups. We used a stratified random sample in order to gather the data. And again, the reason for looking at randomization is 1, we want the sample to somewhat represent the population, and number 2, we want to ensure that everything within each of the groups is equally likely to be chosen. So in other words, we're trying to eliminate or reduce as much of the sampling bias as possible. The third condition deals with the sample size or the shape of the distribution, and this has really 2 parts to it. The first part that we would check is this: is the sample size at least 30 for both groups? So is N1 greater than or equal to 30 and N2 greater than or equal to 30? We have to make sure that both sample sizes are larger than 30. And if you recall from the summary statistics that I gave above, the answer would be no. The group 1, the sample size is 7, and group 2, the sample size is 9. So we don't meet that requirement. So now we have to take a look at the population distribution to determine if it's approximately normal. Now, we don't actually have the population distribution, so we're going to have to use the sample to approximate that population distribution, and we're going to have to check to see if the sample appears to be approximately normal, which would be the distribution is free of outliers, it's symmetric, and it's unimodal. So there's two graphics that we could look at. In this case, since I chose the data and I'm using this as an example, we're probably okay doing this, but I probably wouldn't use the histogram because our sample size is so small, and we have some issues with histograms when we have small sample sizes. So let's take a look at both the box plot and the histogram. Now I'm using SPSS output to create these graphics, and I'll mention a couple things now about graphics when we deal with two independent groups. Number one, I always recommend making sure that if you do a box plot and a histogram, you represent that data with the same scale. So over here you can see I have the same scale on my histograms as I do over here with my box plot. Number two, I think it's really important to use color to help differentiate between the two independent grouping variables. So we had females, I represent them over here in this kind of orange gold color, and also over here in the orange gold color, and I represent the males with this light blue color over here and light blue color over here in the histogram. So that's one way you can help somebody analyzing or looking at your information to differentiate between the two groups, and I think that's pretty important to be able to do. Okay. So there's other characteristics that we'd want to look for too, like the spread of the data, the amount of variability that we see, how those distributions look compared to each other, and other things. And I'm going to save that for another video. For right now, we're just going to look at the shape of the distribution to determine if it appears to be approximately normal. So when we look at the box plot for the females, you can see it looks approximately symmetric, but our median is shifted to one side of the box. So I'd say it's probably close to being symmetric. It would be nicer if the median was in the middle. And you can see there's no asterisks or stars beyond the ends of the whiskers that would indicate any outliers. So for the females, there are no outliers in that distribution, and it's close to being symmetric. Now with the box plot of the males, you can see that there's no outliers in it, so that's a good thing. But the problem is we have some left skewness. You can see the tail that's going down, that's going towards the smaller values, so that would be the left side of our picture if we had it oriented in a horizontal fashion. So we have some left skewness in this distribution, which can be a little bit problematic when we take a look at it. Now over here for histograms, this is technically called either a population pyramid, or some software call it a butterfly plot. I prefer to use this so I can look at them both on the same scale and oriented next to each other versus two independent histograms. But anyways, going back to this, when we look at the histograms for the test scores, we can see that the females appear to be unimodal, and I would say it's close to being symmetric in terms of the shape of the distribution for the females. However, with the males, it's really hard to tell because we've got these gaps in here, and gaps can be a little bit problematic with that, and part of that's probably because we have such a small sample size. The histogram doesn't represent that very well. So if I were doing this in practice, I probably wouldn't use the Unpooled T Test in order to do this. But since this is the only test that we're going to learn about, we're going to say that we satisfy the conditions well enough, okay? So let's go ahead and move on to the next step. So this right here is really telling us, yeah, we can do the T test, and we want to move on, and we want to take a look at the hypothesis statement, okay? So just take a look at the hypothesis statement. Remember, typically our claim comes in the form of H sub A. I'm going to go back up to the problem statement and show you where that comes from. But we want to look for keywords in the problem statement like fewer than, or bigger than, or different than. Those types of words are going to indicate the comparison between the two groups, okay? So let's go back up top and take a look at this. So when we look at this, it says we are studying STEM test scores in education. Would like to know if males perform better than females on average. So the better than right there is essentially saying greater than, all right? And that's a symbol that we're going to use in H sub A. So when we go down here, we're saying that the males right here, mu of group 2, perform better than the mean of females, or females perform worse than males, if you want to think about it that way. So that's H sub A right there, and we got that from the problem statement. So that means H sub 0, we're going to apply the complement rule to it. Now in this situation, I'd probably use the equality statement, but since I teach primarily using the complement rule, we're just going to use that for H sub 0. So we're going to say the average test score for the females is at least as good as the average test score for the males, okay? So H sub A is telling us we're doing a left tail test, so that's why I have this picture over here. Our rejection region will be in the left tail. We're going to be using the t distribution, and our alpha value is going to go in that left tail as well, okay? So now we can move on to step 3, which is our level of significance. So with the level of significance and the test statistic and the p-value, we're going to populate this information in here. So on the left side of this, I take a look at my level of significance, which is my alpha value, which represents the chance of committing what's called type 1 error. That was given to us in the problem statement. And then I have to calculate my degrees of freedom. Remember, I said I'm going to use that conservative degrees of freedom where I look at the minimum of the degrees of freedom for group 1 versus the minimum of the degrees of freedom for group 2, okay? So when I do this, we had 7 females minus 1 and 9 males minus 1. So that would give me the values for my degrees of freedom for the females and the males of 6 and 8. The minimum of those two values is 6. So I'm going to use that value as my degrees of freedom. Just a note, if you were using your calculator for this problem, you would get 10.877 degrees of freedom. That would be the degrees of freedom from using that approximation formula that I showed above, that I mentioned that we won't use if we're doing this with hand calculations, okay? Now our test statistic, we're going to compare the sample statistic, which is the difference between the two means, to the difference between the two population means, okay? So if you recall above, you know, you don't know what mu1 and mu2 are. We're actually just comparing the two. And I have a statement that's written like this. I'm just going to go back up to the top to show you this. But if you recall, we said that when we look at the hypothesis statement, mu1 less than mu2, we could write that as mu1 minus mu2 is less than 0, or mu1 minus mu2 is greater than or equal to 0. So essentially, the hypothesized value of the difference of those two things is 0. Okay, so that's why I'm using 0 in that place when I calculate the test statistic right here. And then I'm just plugging in my sample means for the respective values, my sample standard deviations. I have to square those to get the variances. And then my sample sizes for each of the two groups right here. So it's really a plug and chug to get our test statistic, which we come up with a test statistic of negative 0.494. Now, since that's a negative value and we're doing a left tail test, that's going to be our upper bound. Our lower bound is going to be negative 1 million, technically negative infinity, but we're going to use negative 1 million because the calculator will accept that, okay? So we're going to use a lower bound of negative 1 million, an upper bound of negative 0.494, and the degrees of freedom of 6, and that gives us a p-value of 0.3194. Now, the whole crux of hypothesis testing is to see how different the sample statistic, this thing, x bar 1 minus x bar 2, is from the population parameter, which is mu1 minus mu2. Recall, the bigger the difference between the sample statistic and the population mean, the more likely we are to reject the null hypothesis. The smaller the difference between those two things, the less likely we are to reject the null hypothesis. And so when we go through and we do this, we talked about this before, but the larger our p-value, the less likely we are to reject our null hypothesis, and the smaller our p-value, the more likely we are to reject our null hypothesis. So right here you can see I have a fairly large p-value, which is going to potentially indicate that I'm going to reject or fail to reject my null hypothesis, okay? And so we'll take a look at the decision rule to come up with a formal decision regarding that. So we're going to use the p-value approach. And that's all I'm going to focus on in this lesson and future lessons. But the p-value approach, you'll notice it's the same decision rule that we've used before. If our p-value is less than or equal to our alpha value, we're going to reject h sub 0. And so now we actually have to compare the p-value to the alpha value and make a decision regarding our null hypothesis. So we're going to say, since our p-value of 0.3194 is not less than our alpha value of 0.05, we will fail to reject our null hypothesis. Okay, we're applying that rule. You're showing me what those values are and that you actually compared them, and you're making a decision regarding the null. Step 5, we want to state the conclusion. I like to use really generic statements again. I think it makes it a little bit easier. But we're saying we're failing to reject our null hypothesis. In other words, there's not enough evidence to reject our null hypothesis. So in this case, we're going to say there is not sufficient evidence to support that males perform better than females on STEM tests on average in the population. So this is H sub A in words right here. That's why I'm saying there's not sufficient evidence to support our alternative hypothesis, okay? Hopefully that gives you enough information to kind of understand hypothesis testing for two independent population means using the Unpooled T Test. Later on, we'll take a look at what we do when we have two dependent samples and some other situations as well.